There we go. Building energy metrics and energy modeling. So we've done our VDC recap. And so what I'm going to talk about is why energy modeling and energy metrics, and then talk about energy metrics and energy modeling. The VDC recap. VDC is to the use of multidisciplinary performance models of construction projects, including their products, organizations, and work processes for business objectives. So we have models. I think everyone's pretty clear on that part. That's kind of the easy part. We have the people, which is the part a lot of people don't see in VDC. And that's probably the part that's most difficult. We have the construction, which I think we talked about that as production management. And we have business, well here it says business use, but the business objectives. And I think this one here is the one that's is the least clearly defined in this theory. And then we have measurable metrics of performance for all of these. So let's just take a minute and let's kind of talk through this a little bit. I think, you know, you see this one graphic a lot, and I think we can't talk about it too much, is to understand what do each of these points mean. So yesterday I learned a new term from John called popcorn discussion. And that's where anybody just says something out loud. This is where I'm learning how to teach. So the popcorn method. So who wants to talk about client business objectives?
Just comes down to revenue.
What's that?
It comes down to revenue. Revenue for the company.
Revenue for the company. That's it. So how do you you know, define business objectives? And who defines what those are?
Stakeholders.
The stakeholders. Well, in this case here, the stakeholders I think are more the integrated concurrent engineering phase. You know, when you get to the client business objectives, it's not necessarily collaborative. That's one of the things that's, you know, VDC theory doesn't say to define what we build, deciding what we're going to build. We're going to build a highway, a bridge, or we're going to build a school. VDC doesn't, I didn't see anything in VDC about that. Did anybody see, how do we decide what we build?
I guess it's going to be sustainable multiple operation.
Right. But how do, let's say if you have $1 billion, are you going to build a hospital, a school, or a hotel?
What? I guess I have to toss someone.
Right, because that's VDC. It doesn't tell you how to make that decision. That's a decision that VDC just says, that's the client business objective. And you say, well, how did they come up with their objectives? VDC says, I don't know. They just did it. Somebody shows up at my door, they knock, they walk in, hey, Forrest, I'm going to do a VDC. I have a business objective. They just walk in, I'm building a hospital. I say, why are you building a hospital? They say, I just said, build it. So I think that's something important to understand. You know, when you understand the theory, is to understand, you know, what is the theory, but also understand what the theory isn't. So VDC doesn't do public policy. Pretty simple. You know, if you're a city council or, you know, some kind of public policy group, you probably aren't going to look at VDC to decide what are we going to build. You might want to, you know, try and reuse VDC, but you would be definitely out in new territory of just being, does this work?
But regardless of what you're going to build, your objective is a successful project.
Yes. Well, I don't know. Some owners, maybe they don't want a successful project.
Oh, come on.
High-speed rail seems to be really pushing the limits of that. I'm not sure what they're trying to do. There is money there. So the project objectives is definitely usually to build, you know, a sustainable and good project. And I think everyone can agree on that. So who wants to take integrated concurrent engineering? Yep.
Okay, so ICE is a process where architects, right, engineers, project managers come together and meet in order to create a schedule to detail what should be done this time, when should end, when should start.
Correct. And so at the integrated concurrent engineering meeting, what are some of the goals that they're trying to achieve?
Attendance,
Attendance?
you need to have some percentage of attendance.
That's actually correct. That was what Talika said, yeah. Hey,
Yeah.
oh, fantastic. And that was something that wasn't in the presentation in the previous years. That's because Talika has actually done integrated concurrent engineering meetings. And that was one of the things that she found was important, is attendance. And she tracks attendance as a metric of performance for her meetings.
Would it be as well as to be prepared, bringing like the information on the table? Because if you're there, but you don't know what you're gonna say or what you're gonna do, if you don't have any plan, then there's no point you being there.
That's a good point.
So it's also being prepared, I think.
Yeah. Being prepared is definitely a good idea, because if you don't have the BIM, and bring that to the meeting, there probably won't be a whole lot of flash detection, of looking at the model.
Yeah. I assume there'll be some changes, on the meeting, and maybe this will work, so, but at least having something on the table that can help them.
Okay, that is definitely important. Integrated concurrent engineering aspect of VDC, how do you include the construction workforce? That seemed to be one of the boundaries of VDC as well. Does VDC include the construction crew? Is it the designers? Or what if I'm the city council and I'm not happy with the project? Do I go to the VDC meeting? Is that where I go to be heard as well?
I think so. I mean, it needs to be everyone involved to have a finished product.
So presumably you would have the city council at the VDC meeting as well.
Will you have the client in there too?
I think the client usually is there, yeah, they'll send a representative. I've seen some of these nice meetings. Yeah, that'll be the client rep.
So do I go to City Hall where I say, I want to build a hospital, have revenue, and I want to, like Marcus Love, I want to build a hospital. Does he go to City Hall and submit his approval plan, or how does that work?
That essentially, that is probably another proposal.
Yeah, I mean, even, when they were doing the Apple projects, Gates went right into the city council and said, yeah, I want to get this, approved to folks here in Cupertino. And he sat through many city council meetings.
And so I think it would be interesting to invite the city council to your high school. Do some integrated concurrent engineering, and you can solve public policy issues right then and there. Stanford University right now is in the process of renewing their plan. So they've essentially gone to the county and said, we want to build some new buildings, and they're asking for approval, and the county is going through a long process.
I meant Steve Jobs.
Steve Jobs?
Yeah, it went, for the Apple
For
project.
the Apple project, right. But right now, Stanford's at it.
Yeah, I was like,
I get it mixed up.
But I didn't.
I said Gates, but I was thinking Steve Jobs. Too early in the morning.
So maybe if Stanford said, we're going to follow VDC and we're going to have an integrated concurrent engineering. And Stanford says, we're going to bring all the experts into one room. Stanford could hire me to run this. And they could hire Professor Fisher to come in, they could have a moderator, they have boards all across the room. And one of the questions that the county asked Stanford, what is your maximum buildup that you're going to have? And now that one question has taken 2 years for Stanford to explain that they don't want to answer. They don't know the answer. But if you brought all the experts, you had a dozen experts in one room, all very confident, with a good, somebody good at having everybody, you know, helping everyone to work together, I think somebody could come up with the answer of what is Stanford's total build out. And you can probably have the answer in half a day. I don't think it's like a complicated question. I think it's a complicated question if you work with one person, I take their study, and I hand off a piece of paper over here, and you do the study. I take that back over here, and you do the study. Then I go back up to the policy maker, and I tell them. That's a very long process. And I think this is probably somewhere where an integrated concurrent engineering approach would work is something that's very complicated, like public policy. Product model, the BIM.
It's software based, right? Where you use rather the scheduling software.
Yes.
Call it LS. Or something like that, right? Use software to detail what how to build the project.
Yes. Absolutely correct. So where do you learn the software?
I mean, like on your lectures.
That's exactly it. You don't take other software. And that's one of the things about VDC is also VDC doesn't have a lot of software. But, you know, you're both from the CAD program. I'm sure Dennis has probably used some software, Song's had some software, you've probably learned some software. No. And you bring those software skills with you. And if you need to learn some new software, you know, let's say Dennis needs to learn how to make a schedule. Just go online, I want some scheduling software. Scheduling software comes up, teach yourself on the tutorial real quick, scheduling software. So I think if somebody wanted to ask, why is VDC not focused on learning the software? Does anyone have any idea why? I mean, we could teach the class where we could just take 24 softwares. You're gonna learn 24 softwares and be experts with them. That could also be this fun. Could all be our lab computers, take it away the whole week.
I think you mentioned the early days of this class that VDC is not BIM.
That's right. BIM is part of the VDC, but it's not BIM. Anyone have an idea why there's actually kind of a theoretical reason why the software is not part of the class?
It's about people and corporate enterprise to make the project become a reality, and we use them as a tool of BDC, but then it's not BDC. So BDC focuses on stakeholders' the actual project, the actual part.
And those are like the sound bites we throw out there, especially early on in the class to like really get people past that software stuff. So I can give the answer. So the reason why VDC doesn't focus on the software is because its assumption is software doesn't take any time to learn. So like, you know, Google, if I wanted to search for something, how many do I need a class on Google? No, there's no class on Google. Before Google, there used to be actual classes on how to search. And you would get like, I think there was even maybe a university degree in searching for data. Wasn't there? I think there was. It's like a librarian or something. You know, this was like a whole field of study. Google destroyed it overnight. Just type in the search term, there it is. So the idea is, even though today, like I know learning CAD is difficult. Like it takes, how long does it take to learn CAD proficiently? How many years do you think?
1 year? Or
Yeah, right. A year. But someday in the future, it won't take a year to learn CAD. The software will get better. And so there's a whole theory, there's a whole domain of work in the computer science world, working on theories of how to make software easier to use. And in the best case, I should be able to pick up any software and just use it without having to necessarily know anything about the software. So the focus of VDC then is to teach you the concepts that the software is going to have. So You know, let's say I want to do an integrated concurrent engineering. Because that was the last one we kind of picked up. How many software would I use for this to do this?
Just one.
One? What software?
Just go to Zoom and have everyone together.
Okay, there's one. Is there another software to use?
Social media, that's pretty much the same.
Right? Is there another software? Okay.
Yeah, okay.
I could use all kinds of software. And do I need, you know, how long do I need to take to learn Zoom, GoToMeeting, Skype? Right. So I could do an integrated concurrent engineering session virtually and present using probably, there's hundreds of different software that I can use. None of them do I need to actually specifically know. So that's where, if I know how to hold an integrated concurrent engineering, like I know I need attendance, I'm going to take attendance. So I'm going to use some attendance software. I know that I need to probably have people be able to try it virtually. So I'm going to have like Zoom. I do know I need probably boards that they can write on. So maybe I'm going to have some Neurova boards that have, you know, that I can write on like we had at the site. I haven't seen, there's probably going to be BIM. It's going to be there. There's probably going to be like a Revit with a 3D model. Probably like a lightweight type of Navisworks thing where you rotate the model. I'll probably integrate current engineering. We'll probably have a virtual reality corner where I'm going to put the goggles on. I'm going to walk around and look at whatever I'm building. You know, there's going to be a large number of software. None of them am I going to particularly spend a lot of time learning. Let's see. Project production management. I think this one was one that really was, over the last week, it had the most people asking questions about. And there was the most confusion. I think Daniel Garcia, the labor representative from the roofers, had a different concept, project production management, from Mike Williams, the Project Production Institute, you know, theorist. Fundamental, I don't think either one of them completely quite were seeing what the other one was saying.
Oh, can I take a guess?
What's that?
Can I take a guess?
Yeah, go ahead.
Okay, so I think project production management basically incorporates the production organization process matrix, model A, where you list the form, function, behavior, basically for those 30 minutes.
I heard form, function, behavior, product organization process. Is there, we had variability, we had the dice game, we had the airplane game. We looked at different ways of paying people for motivation. You know, you pay people piecework, you pay them by the hour, you pay them by batch. And project objectives. We'll come back to here. That's the last one. I'm guessing, I think that's measurable. That's the metrics. Measurable metrics is the project objectives. Take away this one here. There's a few different versions of this slide. Is that project metrics? I'm actually not 100% sure. So with these concepts, then if we apply this to energy model, so let's say the client business objective is, I want to have an energy efficient building. I don't want to spend money on it. Then, you know, say my business objective is, I don't want any energy costs. I think energy costs are going to go up in the future. I want to be isolated from that. There's objective. Project objective now is design an energy efficient building. Integrated concurrent engineering, we're going to have everybody come together and we're going to have the window expert, the insulation expert, the roof expert, probably the ground thermal expert, the heating and air conditioning. You have a lot of different experts come together. Now it's going to be a global warming expert that's going to be able to forecast what's the climate going to be in this, where this building is in the next 100 years. Use modeling tools. You can imagine all those different experts. Each one has their own specialized tool, maybe 12. And then project production management, we're gonna actually build this building. And when we build it, we need to have a way, how are we going to construct this building? Are we going to pay people piecework? We're going to pay them by the hour? Are we going to pay people by batches? Are we going to pay them by smaller pieces? These are all the questions of how are we going to set up this project so that it's built to the level of quality to achieve the objective. So why energy metrics and energy models? I think this one here, at this point in the class, should be pretty easy. Anybody take that one?
I think the energy metrics, energy modeling, is used to try to try to accomplish the project objective.
It could be cost, but think of the experience we had at Stanford this week in that building during the heat. I think that one there, they probably did optimize for cost, but wouldn't we have rather if they had optimized for comfort? And they had said, no matter what happens, this building will always be habitable by humans. Because I think at one point we actually should have all left the building. It was simply not healthy to be inside that building at about noon on Wednesday. I found out later yesterday that Roger had looked at it. He had a CO2 sensor, and he had something on his watch that was recording, and he had looked, and he said it was 2,000 parts per million in that site view room, which is just unbelievable. It's impossible. If I had known that, we all would have left.
What's the safe level was around 800.
Yeah, 1,200 is the design level. 800 is the level where cognitive decline begins. So everything past 800, everybody was paying attention that much less. So I think by 2000, we were probably all understanding something like half of what anybody was saying.
Would weather be a factor?
What's that?
Would weather be a factor? Say if I live in Florida, I know it's hurricanes, I would design something that would be hurricane resistant
Yes.
so that it wouldn't impact just where I live or something.
That's absolutely correct. And the modeling software, you can place the building wherever it is, run the energy analysis over an entire year. Every minute it'll say, okay, this is what the temperature probably is, and it'll calculate what the temperature inside the building is. And the next minute it'll do the same thing. It'll do that for a whole year, and then it'll give you a estimate of what's the energy needed to keep that building heated and cooled. And so it's usually site specific. And if it's a hurricane, then typically hurricanes come through. It's going to model a hurricane going through as well and say, okay, what's the heating and cooling load during a hurricane? Let's see. So these are the VDC objectives and metrics, which jump back real quick. I'm pretty sure that's the project objectives. They're using a slightly different term. So this isn't something new here. So the VDC objectives and metrics. So we have cost, schedule, facility, safety, design, delivery, management, and communication. So this is interesting because safety, that's something that showed up in VDC more recently. And I actually like seeing that is in this slide. What's interesting here is it doesn't include scope. It just says cost, schedule. So it's a little bit interesting. So here's some things you can measure. Where we have delivery design, facility. So this doesn't have the ICE meeting, but in the ICE meeting we know the metric of the VDC objective is to have to measure attendance. So here we're getting into the energy metrics, energy performance. So this lecture here, we're going to go dive down into the energy performance of the facility. So building operation accounts for the majority of the life cycle of the building. So why does anyone have an idea why that is? Why does the use of the building account for 80% of the total cost of the building? Because the building's built. You know, isn't that where you spend all the money right there?
No.
So where's the cost over here?
The life of the building.
How much is going to cost to sustain that building and that operation off of the site?
So that's where you have the cost that's the energy, where you're paying for electricity, the maintenance of the building. So it turns out that when I first started at Stanford, a lot of the focus was still on the first construction cost. But a lot of people were understanding that really the biggest cost in a building is over here. I don't know if that's the same as true for, say, a highway. If the maintenance cost of a highway is 80% of the total cost of building the highway, but it's possible. You can probably build a highway that's going to cost a huge amount of money to maintain versus the initial cost of it. But in buildings, it's pretty clear because they use energy. So a power plant is probably something else that the way you build the power plant changes the total cost. And you can make a power plant that's very expensive to maintain or a power plant that's not as expensive to maintain. So that means that when you're designing the building, you have to focus on whatever you're designing, you have to focus on designing it so that the cost, spending more upfront to spend less during the life of the project, the life of the facility. Yes.
Go back.
Yep.
Do you know how you came up with numbers 20%?
You know, we had that question yesterday as well. Asher asked that. She said a lot of these slides have these numbers, and she says they're not necessarily cited. And so there's no citation on this slide. Usually it would be down here and it would say, you know, Fisher and Cooperman et al., you know, with the year. And so this is actually bad practice on whoever made these slides, that they didn't put a citation on. So something to remember when you're making your own slides. Keep notes and put where you got it. Yeah, also these images. This is saying that the person who made this slide, they took those photos, which I know is not the case. They copied these photos off the internet. What's that?
Plagiarism?
More or less, yeah, and it's not intentional. But yeah, like usually I try to always be very diligent that I will always have in light gray and like 6-point font the website where I got the image from. I just post it right there, people don't even notice it. And if the concept, like it has a big number like this here, I'll put down here where I got the number. So to answer your question, those numbers I think are probably rules of thumb. If you modeled it, if you just took a building and let's say I told you, take this building right here. And I told you to do the cost of it. We know this building costs $4,000 to build. And now I tell you, you know, in fact, maybe this would be your team project. I don't know. It could be. You know, help Mr. Ochoa understand how much is this building going to cost the school each year. But we do have that analysis, don't we?
How much going to cost to run it?
Yeah. They started on it because they have the solar panels. They're trying to make it net zero.
Yes, we have the solar panels, and the actual solar panels that we will install when we build the actual showcase. You know, so this previous presentation was just about building it. Now we have not done an analysis of the building and how much it's going to cost and efficiency. That's going to be our next project. As a matter of fact, facilities is going to work with us. Okay. And we're going to have equipment that's going to measure how much solar power we using on a daily basis.
So according to this ratio here, if this building costs $4,000 to build, which is only material, so if it was including labor, probably imagine the labor is going to be about twice as much as material, I'm guessing. So this, if you paid someone to build this, it would probably cost you $8,000 to pay somebody. $4,000 of material, so this might be a $12,000 building. That'd be probably on the low end of the estimate. but it could be there, it's probably, so let's say this is a $12,000 building, you know that's 20% of the total cost. So you know this building is gonna be, the energy cost is going to be 4 times as much. So that would give you, we would say it's gonna cost $48,000 of the life of this building. Which, you know, if it didn't have solar panels. So that would be just, for me, that's called the back of the envelope estimate. I made up all those numbers. I say this is a $12,000 building with a $48,000 energy cost of the lifetime. Is that true? I don't know. But it's probably in the ballpark.
Actually, go back to that a little bit. One thing that the students did do, they did calculate how much electricity was going to be produced in the solar panels that we have. And they kind of guess what equipment is going to be there, subtract that from what we get in. But we have not done the actual study because we don't have, how many fans, what kind of TV, what kind of pumps we're going to, what kind of pumps are going to supply power to the aquatic system. So that is part of the next phase. So they did do an analysis, but not with our actual equipment.
I should put a sticky note on it with my estimate. And then we'll see how, put my phone number on there. Yeah, when you have the final numbers, call me. How close was I? Am I off by 100%? Is it actually going to be a $24,000 building with a $96,000 energy cost on the lifetime of it? Could be. Is it going to be a $6,000 building that has a $24,000 energy cost? Is it going to be half of what it estimated? So I could say, as an engineer, I'd be like, cost of this building is going to be somewhere between $6,000 and $24,000 to build, and the energy cost of this building is going to be somewhere between $24,000 and $96,000. And if I gave that to the principal and be like, is that in the ballpark of what you're expecting? He might be like, yeah, that's good. He'd be like, okay, let's go build it, and we'll see what it actually is. So that's where the ratio comes from. It's probably just, when you pencil out the numbers, they just always kind of come out as a ratio of, 80-20.
Good question.
When you say life cycle,
Mhm.
how many years are we talking about? Is it by years or how many years? Is
Really,
it-
really good question. Yeah, go ahead.
Well, that's the same thing, it doesn't say 50 years or 100 years.
Yeah, Dennis was talking about, they were tearing down buildings he built. And he's like, we built that building to last 100 years, and they're tearing them down after 20 years.
Well, more like 30, 40 years.
And so that concept of what is a building life cycle has changed. When I first started at Stanford, it was 30 to 50 years. More recently, in the presentations I've seen from the students, that concept is stretching out to 100 to 500 years. 500 years is so far out that people don't take that seriously. But I think the software is allowing people to more reliably forecast a building out further. But it's definitely a big limitation. I asked a student as a teaching assistant, I said, it was essentially this class that we're in. It was like 10 years ago. I asked a young woman who was a student from Germany. She had flown all the way into the US for the class for the kickoff, and I was her teaching assistant. And I said, I want you to do the energy analysis of that building for 500 years. And she was so mad at me. And she argued with me, and she says, that's ridiculous. She says, it's impossible. And I was like, oh, it's not that hard. I said, well, look, the wood framing probably, like the heavy timber probably is 500 years. And I just did it real back of the envelope. And she says, well, that's great. You can stand there and just do that. But she says, there's no software that'll do that. She says, I can't forecast anything without the software. So that concept is changing with the software. So energy metrics. Why do energy metrics matter?
Maybe to determine if you're using too much energy.
Yeah.
Environmental impacts.
Calculate the environmental impacts.
Cost.
There we go. Take 3 minutes to brainstorm. 2, 2, and 2. Okay, we'll take 3 minutes. I'll set the timer. This is my colleague Alyssa's presentation.
No, that's fine. Hey,
you-
Forrest, I'm having a hard time seeing your screen. It won't, now it clicked on.
Okay, you can see the screen.
Yeah, it just now clicked on the, you know, your screen with your matrix and everything, your PowerPoint?
Oh, I'm not on this.
It wouldn't click on till just right now. Now it's a black screen that you just clicked.
All right, thank you, David. That was good feedback. I'll open up the screen in a different way. So, okay, I use the presenter view, and somehow Zoom doesn't pick up.
Okay.
We're doing energy efficiency.
There we go. There we go. Okay. We are.
Town Ford plant? That was NUMI. It was the Ford plant, the NUMI, or no, the GM plant. It was a GM plant.
Oh, there was some.
It was a Ford plant.
So why do energy metrics matter? What was the? What'd you come up with?
Yeah, we came up with a few.
Okay.
We said cost, trying to save the planet, energy. For comfort, time, you know, if we gotta fix it all over again, so something went wrong.
So comfort time, that would be the building finished. Let's see, sustainability goals, that would be where you said save the planet. And what was the third one?
And time.
Time. The time to meet, building up a tip for building, let's see. Well, that would be project team of getting the building quick time. How does energy relate to time?
Well, in my perspective, I saw it like, if you don't do it right the first time, you may have to come back a few years later and try to fix it again.
Perfect.
Or how long it's gonna take, trying to create something new.
Right here, meet the building's intent for building energy consumption, because if you don't meet that, you're gonna come back and have to rebuild it. Okay, is that those three? Okay.
So yeah, it's whatever the, owner objective is,
Okay.
if, he wants to be, environmentally conscious, is he willing to spend money to do that?
Okay.
Or how much can he actually afford? Maybe he wants to do that, but he's, confined by the cost.
Okay. Perfect. Did you come up with the 15 or David? I heard numbers over here.
Yeah, I don't know how we got to numbers. Why does it matter? Comes down to cost and
Okay.
energy efficient.
What was the example you worked out for the numbers? Thanks, kind of curious. What was the?
We did an Energy Star compared to a common
Okay.
house. Energy Star, we were able to save 48,000 or 50,000 over a 30 lifespan.
Okay. I see what you're saying. So 50, how much over the first one?
About 50,000.
Okay, so
And
that's
this one.
why it matters. That's a very, numbers driven. It matters because it's literally a difference of $50,000 over the course of life of a house, which is interesting because if you're building the house yourself, that will literally pay for the house because 50,000 material will pretty much get you the house. Okay.
Right, the one thing we didn't get to was how much it costs to put the energy efficiency house together. We didn't analyze that.
Okay.
For the real savings.
Yeah, he had an example. He told me that, I guess they estimated a project.
Yeah.
And I guess when they said yes to everything, but when they started the project, they didn't estimate the energy cost of how, when building the material, bringing the materials in,
Yeah.
the tools they were gonna use. So that was extra money the client didn't have. And it's like, okay, what's happening here,
Okay. That's a big deal.
So,
Yeah. What was the solution?
They using a plan for making energy for the project
Okay.
and extra money.
They had to pay extra.
Yeah.
Okay, so building performance metric. So which building operator should get a Christmas bonus? So there's two building operators. There's operator one,
And they show that in 2006 to 2007, they reduced their energy costs. And in building 2, in 2006 and 2007, their building costs went up a little bit. Now, somebody noticed last year, they're like, well, what if this was a cold year and that was a hot? And we're like, okay, you know, in this example, imagine it was essentially the same year to year. And a lot of the more interesting things that have been built at site, we have been looking for hidden performance. That when you look at something, you know, with just looking at just, you know, the total cost of something, oftentimes will hide the truth. And that if you look at something as a ratio of something else, you start to see the truth. So it seems like the blue building is performing poorly. And it's using twice as much as the green building. Everyone see this? Take 3 minutes and with partner, brainstorm, how do you know how well a building performs? And I think I'll give you a big hint, is look at ratios for occupant use. Not sure what the other ones are, but one metric I do know that's too advanced for exactly what we're doing here, but just something to keep in mind is that as a building gets bigger and bigger, at some point, it's going to just simply use less energy per square foot simply because the building is so big. You know, a small house is essentially going to be inherently somewhat more energy consumption than a big building because it just takes time to heat that house, have all the energy in the house. But if you have a massive building, heating each one of those square feet isn't necessarily costing much. And so if you take 2 buildings and compare them, a building that appears to be inefficient is actually just a really big building. And it's actually more efficient than what it looks like because you would expect it to be, have a different efficiency based on the size of the building. So take 3 minutes, I'll set the alarm, and just try to be creative on how do you determine building performance.
So with what you were saying, I mean, is that because of like the ambient temperature of, you know, what's going on outside the building versus inside the building? You know, in a small building, you're trying to control it more. In a big building, you're kind of going with
Yeah.
I see it. It's okay, I got it.
Sun and High, are we a team?
Yeah, let's let you go.
Is that the booby trap, just in case somebody comes in? Okay. Let me redraw the one more because I'm redrawing. American Gaussian uses for the heat. He took energy records for a whole region of Ireland. Might have been all of them. He got a hold of the data set. And so when he looked at buildings, and I think this was like, I think this side here was energy use, and this was building square footage. Well, it was Ireland, so those are square meters. And he had basically, as a building gets bigger, you have to use more energy. So essentially you had, you know, here's the data set. And so what he wants to know is what is the optimal efficiency. If this and you model it, you would say simply, there's the line, these are bad buildings. And these are good. And at that point, pretty much everyone's, and so you say all these bad buildings need to be improved to become good buildings. And you're not going to take the building and, you know, reduce the square footage. So what you have to do is you're using too much energy. So you want to take that building, make corrections, and get it below the bar. And so let's say I am in the city of San Jose. I want to identify all my housing stuff that's using too much energy. And I know that these citizens are paying too much for their energy, and I don't want my citizens spending all that money on energy. I want them buying food. So I'm in this city, I'm just going to go through and say, I'm measuring every building, all the houses that are using too much energy, and me as a city, I'm just going to go out at once, and I'm going to fix them all, so that way everybody living in them is paying their money on food and on energy.
Uh-oh, did I lose you guys?
This seems like a good idea. Okay. Sorry, David, I'm off the, I think I'm off the over here. You can see me somewhat. So Amir, do I have to say Amir is one of those people that's inherently brilliant. He sees things that nobody else does, and he's pretty subtle about it. So what it turns out is that when the building square footage gets out here, because the building is so big, they just stop using more energy. And so you look at buildings out here that appear to be good buildings, but they're actually bad buildings. Because you've gone so far out on the square footage that, I mean, essentially, you know, if you take this building right here, you got a massive building, it's good. But because it's allowing it so much energy, because you just project it all the way out, this building is allowed to use some astronomical amount of energy. And so what Amir found is that this actually looks like this. And so he found that some buildings here that actually look like bad buildings weren't bad buildings. They were actually okay. And buildings out here that looked like they were good buildings were actually not good. And so a lot of people like this curve because he just had said, no, all these buildings in here are actually okay. You don't need to go out and improve the performance. It's just the size of the building. They're going to inherently use more energy per square footage. And the huge buildings are going to use, they kind of, at some point, you just don't need to put any more energy into those. It just uses that same amount of energy.
If you're trying to control the environment in that space,
Right.
the amount of energy it takes to control the environment at whatever level.
Air conditioning. Probably messed something up on that, but that's basically the idea, is that it's a little bit deceptive. You know, I'll give you this maybe as an example of like the most common. When they went to Stanford University for facility management, they're like, no, we like this. And they actually refused it. They just didn't quite get it. Amir was really well at explaining it, but the problem is he's really intelligent. He can explain it and I can understand it, but if I go to explain it to the next person, they're kind of like, you know, and the theory is so complicated, there's like 3 people in the world that can explain it in a way that's understandable.
I somewhat understand it because, you know, the requirements, you know, on that large square footage, you know, are, you're allowed, you know, a certain amount of energy usage, right? And you're using that to cover a larger amount of square feet, so it kind of makes sense.
There's something in here I think I'm missing. At some point, you're like, if the building is bigger and bigger, of course it's going to take more energy. So I'm not sure why it plateaus at some point. And it doesn't make sense to be like, oh, it's never going to take any more energy. So I know I'm missing something been 6, 7 years since all this traffic, but this is basically the idea is that there's different ways of looking at it. So instead of working with partners, everybody was listening to me, draw my graphic up there. Now I'm going to take a look at it. Okay. First, brainstorm. Okay.
We said, so how do we know which building is performing better? If the inspection keeps passing,
Okay.
so if they check it each year and everything is good.
Inspection. How do you know if the building is performing?
If the people operating the smaller building are using more energy, let's say, than the people use the big building, where there's more people in the small building, and the production is actually it's more efficient, even though they're using more energy than the bigger building.
Okay.
So the output is, but it's more for the one that, for the smaller building that's using more energy, and you compare the ratios, the building producing less, using more energy, the ratio is bigger
Okay.
than the big building.
How do you tell the buildings?
What was your partner again? What was your partner? No, go ahead, say it.
David, what metric do you use to tell a building is performing well?
Building performance, what metric?
Yeah.
I go off of square feet, and then I figure out how many people are using that building in that square foot. So, I mean, obviously, if you have a small building and only one person is using it, they're using much more energy than a bigger house with 5 or 6 people in it per square foot per person. Does that make sense? It's like riding a jumbo jet as opposed to a single airplane burning up fuel. Does it make any sense what I said?
It does. Income quote. There we go. So this one here is looking at per dollar of benefit. So it's almost like what you're saying, David, of looking at the building per occupant, but also not only that, but let's look at the energy consumption per dollar earned by the occupant. So I think it's clear that this concept probably comes from manufacturing, where you're looking at, you know, how many widgets I produce for the amount of energy that I purchased. And so basically, if you're looking at, you know, the per widget approach, and you're saying that this is per transaction. And so this is now showing us the energy efficient building. While it appeared to be less efficient, if you look at per transaction, it's now performing the same each year. Whereas the normal building is not as efficient, it's half as efficient. If you look at it per transaction, it's not producing as many transactions. I think the example where they found this is in Japan, or maybe it was Korea. There's a culture in, I think it was Korea, that if you walk by, it was a Disney, so I'm pretty sure it wasn't Korea, it was Shanghai, Disney Shanghai. Disney Shanghai had buildings that were like off the chart of energy. And so an energy consultant came in and looked at this, probably Stanford student, and said, you know, why are you using so much energy? And they went there and the doors were open to the store at Disneyland. And it had all the merchandise. And they said, oh, well, you need to close the doors to reduce the energy consumption. And so they did, but when they closed the doors, what happened was their sales dropped. And so they were kind of like, well, what's the point of closing the doors to save energy, and now we're not selling anything? And so they said, okay, and I think they tried some different things of putting like a revolving door. I think they had like kind of a curtain type door, you know, the things that you walk through. They tried different things to kind of keep the energy inside the building. And no matter what they did, the sales were still down. And at Disneyland, that's what it's all about, the sales, merchandise. And so what it turns out is that in the US, it actually wasn't that big a deal to have the doors closed. People just walk up, they open the door, they go in. It turned out in the culture in Disney Shanghai, when a customer walks past the door, the blast of cold air is what makes people go, oh, you know, and they go in there. The building literally had to have cold air blowing out the door for people to feel that this is the place where they wanted to shop.
That's true.
It's true.
That's true.
Okay, I've only heard this story, so I'm reciting it. It is. Can you share anything on this? Because I never. Yeah.
Well, whenever you go to any mall or so, when you walk by this cold air, I'm going to go in. It attracts me to go in there already. And when I'm in there, it's like, oh, hey, this looks nice and nice. I'm just going to go get it.
Okay. So they had to take the doors back off all the buildings. And their profit. And so I think that's where this graphic came up. Is even though the building is using more energy, it's doing better per transaction. It's generating more revenue. And so that way you would be able to see the real value of the energy consumption versus just the building as simply using more energy. There it is. The green building performs poorly. The green building has doors, whereas the non-green building does not. I think I got lost in this pictures a little bit. Luckily, I heard the presentation. Okay, so project building performance objectives. So once again, this is showing. There. So what is this showing? Popcorn stuff. Well, first, this here is cost, and this is time. We have time, and we have cost. So this time frame here, what cost is being represented by this law? Good.
Cost of gathering materials.
That's right. This is the cost of building. Labor, material, and equipment. And now we define yesterday, and safety. So the cost of the labor, equipment, material, and the safety involved in building that. So this is below the line, which means these are costs. So this cost here, this is the life of the building. Now it doesn't say 50 years or 500 years or 30. But at some point, the building life is done. So what cost is this here with number 3?
This cost that you need to repair faulty equipment.
That's right. And to pay for the electricity. Yes. So this cost right here, I think when you're going back and talking about the doors being open on the store, this is the business operation cost. And so we open the doors because that's a cost of business. It's okay that the building isn't efficient. If I gave another example here of a building where you say, hey, we don't want to be as efficient, and the example is help. So one of the examples they used to give is that energy retrofits would go into a building, say like this building here, and they would seal the building. You know, this one does that seals on the door here, and let's say you blocked off the doors back here, and we sealed this building. And then what we did was we removed the fresh air going into the building and just put a recirculator. And what we would do is we would create a building that would make everybody sick. But the building would cost, the energy cost would go way down. But while we're making an energy efficient building, we're now increasing the cost of people's health. And that's a lot like this, the Shanghai. While we're decreasing the energy cost, we're also eliminating the revenue of that building because nobody wants to shop there. And so this here is where you look at the income from the building. And so what is the income of the building?
Money from the transaction.
There you go. So like even this building right here, what's the income for this building? What are the widgets?
Students.
That's right. We're the widgets. And we are the product. We are the income. So this building right here, if we looked at the energy consumption of this building and follow this model, we would say what is, well, in this case here, it would be per student. It wouldn't be the occupants. It wouldn't be, say, the lecturer. I'm the same as, you know, somebody couldn't tell the difference between me and the chop saw of a piece of equipment. The students are widgets. So we would look at what is the energy cost of this building per student. And then we would chart that and look at each one of these buildings. So let's say Roger and Matt were in the safety program all last week. Right now, they're probably not looking at the buildings. They're probably looking at the energy cost per square foot. I know they're also looking at the CO2 levels, which probably actually going to give them a better measure. But let's say they, instead of looking at energy costs of the building per square foot, they look at the energy costs per student, excluding the faculty. And then said, what is the energy cost of each building? And they probably would actually find some buildings that use a lot of energy inefficient are probably actually per widget efficient. So, yeah, looking at the income as a component of energy efficiency and not just looking at what's the cost of designing the building, what's the cost of operating the building, what's the business operations cost, but include the income. And again, if you look on here, you're like, okay, who came up with that idea? You want to tell me who made this concept? No, we have no idea. It has no citation. And I will bring that feedback to everybody and say, hey, we really like these presentations. But they were like, who made that? What to say? I don't know. Okay, how do you define building energy performance? Okay, so with a partner, again, now we're going to take 5 minutes. And then we're going to take 10 minutes to discuss, and we're going to consider how do you define building energy performance considering building use type, level of service, the climate, and the operating hours. And then next, we're going to go into incident model.
Just a short comment. For the first time, I was looking at your shop when you guys were working. The first time I was just paranoid. I guess maybe that 3 kid. I was looking at all the equipment here, and I was like, this is just terrifying. This classroom. I mean, every one of these is incredibly dangerous. Mm-hmm. And I was just like, and you sit here, and you have all these students in here, and none of them can they cannot get hurt, right?
That is our goal.
Yeah.
And yeah, I mean, kids are pretty good. They know that in the class, they're allowed to make mistakes. They're allowed to catch something wrong. That's fine. And there's no repercussions for that. Safety, though, that's one thing that we do not tolerate because the 95% on a quiz and a test is really good. But like a construction teacher used to say, he used to go like this, 95% is not good at construction. So yeah, my students are very conscious. We go through every tool before they get to use it. There's a safety briefing. We go through the tools. Everybody gets to use it. Strongly and yeah, safety is a big. You're right.
And you're alone. You don't have another assistant or anything.
I'm alone, but the students,
That's the part that makes me
yeah, the students, once again, safety is very important. So make sure that everybody is on the same page. When
I
it
know
comes out
where
to safety.
it is like the emergency packet of the like first aid, know what that is. And,
Yes,
they
and
could
also
go and quick grab it and.
the thing is, we don't want to use it now. We don't want to get to that point.
That's true.
So prevention is the big thing in this class. And technology is also helping us. To give you an example, that tail saw repair. If you cut it with the tail saw, you touch it, it's going to drop. It's not going to touch your finger. It costs like $80 every time that happens because there's a mechanism that pops and drops it. You know, $80 is really good for
To save a finger.
to save a finger. And actually, yeah, and sometimes it also senses moisture.
Yeah.
So it doesn't have to be your finger. That creates a problem. So let me show you this real quick. Hope I'm not.
No, go ahead. For safety?
Yes.
Okay, safety.
Okay, so
Safety meeting.
OSHA.
I had a, PTSD triggers. Take a safety note.
our principal, he's really good with tools, and he works with practice and stuff. So somehow, this is what happened. This is the blade that goes in the chop saw. It sends sometimes moisture, water. If you touch it, it'll be a minor scratch, but it's not going to cut your finger. So this is what happens. So he triggers his sensor, and you can tell how it stops the blade. So it stops the blade. So it stops the blade in like 1,000th of a second. I'm not sure I'm going to give you the number, but these drops are that. So the problem with this, like when this happens, it's a lot of fun to change the things, right? So technology is helping us with safety. Goggles is a must. Doesn't matter what you're doing. It could be the person next to you, this is using a chop saw, take back the small piece of something, hits your eye, not good. So yeah, safety is very, one thing to be very cautious in this class.
Remembering, as a student in the shop just like this, they all kind of look the same. Same desk. I don't know who made these tables, but every shop has this. Is the trust that goes into, now I'm thinking if there are students in here, after a while you start getting, okay, I trust them, and you start letting them have more freedom, which as a student is, you have the freedom to work with incredibly dangerous tools, but you have that confidence to use it. And I remember my instructor having that trust as where, I could go over there and we had a welding booth and I was free to just go weld on my own. All I wanted, the instructor just knew I was okay over there because he trusted me to use the welding equipment. And it takes some time to build that trust up. It's a good program, the shop, environment. So this realizing this class here mixes with that actually pretty nice. But at the end of the day, it's all about safety too, which EC gets lost when you get to the.
Is this class as an elective?
Yes, it is an elective. However, it is A to G approved,
Oh, okay, that's good.
but yeah, it's an elective.
You also show them how to use a miter box.
Ladder box.
So you don't even know. Miter box is, is a jig set up with a handsaw.
The angles, right?
Yeah.
You know what we're showing? We don't use the hand miter box then. We have a little chop saws.
Well, that's what I'm saying, but from a safety standpoint, you can still get that piece of wood cut with a handsaw and a miter box.
I think it's more cost efficient. I think that's we have it in the construction building, the Microsoft box. I think there's a lot of money for that one. 8,000 or something, just like the size of this one right here.
For a hand?
No, actually, no, I think we have a miter saw, and then the one in the construction buildings where I think it's building 112 or something, where you just machine it.
You guys are making me feel really old.
It's probably a nice one. I know the one you're talking about. When I was a kid, it was in the garage, you pulled it out. I used to use it all the time. It's got a special little square, a rectangular saw.
Put your piece of wood in there and you can cut any angle on it, and like you say, it's a handsaw.
You talk about the chop saw. We talked about the version where it's like the thing you put your wood in here and you got like slots.
They still call them miter saws now, the
hand miter saw.
powerful, but back in the day, where, that's what carpenters had, when they want to make accurate cuts, they use a miter box. And you could set the angles of your saw at anything that you needed.
Gotcha.
It was a fine-tooth saw, and you could cut any angle that you need on a piece of wood.
Yeah, so I see exactly.
So from a safety standpoint, I mean, you can get the same piece of wood cut. It may take you a couple minutes longer,
I see what you're saying.
but
Versus
the
using
chances
power
of getting hurt are,
Well, I agree with you. However, though, we are in the age that, power tools make everything easier, faster. So why would I teach my kids? Why wouldn't I teach my kids to use a nail gun? Well, that's what they're going to really be using, and it's probably more dangerous than using, let's say, a hammer. So I can say, hey, we're going to go frame our project out there with a hammer and nails, because I don't want you to use a nail gun because you might accidentally shoot a nail to your,
Right, everything's got things. It's industrial.
Yeah, and safer.
And safer, hopefully. But things will hurt you much worse. A miter box, the worst you're ever going to get is a nick.
Yeah,
Unless you're really
exactly.
drunk and you cut halfway through your finger.
Which big right in the middle of right.
so you need to teach more safety now to use the type of tools that we have available,
Oh yeah,
because
totally.
it has actually gotten more dangerous.
I think this goes what's more dangerous and safer. Like the example, the table saw that I just went over. So many years ago we didn't have that. So you had a chop saw, you had a table saw, but nowadays we got a safety feature in it. And like I tell my students, just because we have the safety feature don't mean that don't try to show your neighbors like, hey, look at this, right? Why if that one day the sensor is not working, there goes the finger. So I let them know just because of the safety component is there, an extra safety component, don't ever rely on it. Always think that it's not there. Exactly. Every single tool that we have here, there's a video and a safety briefing that goes with everything, and then you got to take a rating test. And they're not allowed to use that equipment until there's 100% on the safety quiz. And of course, like I said, the quiz is 10 questions. Then it's through. They don't have to take the whole thing. They just got to take those 3 questions, so they understand exactly, the proper way to doing it. So that's one thing that we very conscious, safety. Not only on the resource next door, he's got power tools going on. And I think we're the only 2 classes that really have a lot of power tools, mainly this one. And it is challenging because even though we go to the safety briefing and use the tools and stuff, every now and then you catch a student that, where you got us at, right? Simple things, or, another student that decides to, skill saw, puts a wedge in there so that the guard is not there. So you always you got to be aware. And that's, the best that we can do. We have not had an accident here besides like a spinner,
What about eyes? Have you had people get?
No, I have had twice. I have had no major accidents. And when I said, and the ones that we have had is what I'm saying, something like, splinter, minor things that I expect to happen, but nothing major.
Let's keep it that way.
Yeah, so you're doing the right thing.
And it is challenging because, we got a lot of students working at certain things at the same time. So we got to be aware. And I got students that, if you see something unsafe, you tell that person, you tell me because he can say, man, someone else can get hurt. In construction, we know that sometimes when accidents happen and somebody gets hurt, sometimes it's not your fault. It's the person another person.
Right.
So, you're walking by and somebody goes like this with a hammer and he's not holding it, firmly, the hammer flies, hits you in the face. You had nothing to do with that action there, but you got hurt because of it. So, yeah, and, they're pretty safety conscious actually so far.
Good.
And I'm trying to keep it that way.
Yeah, sounds good.
All right.
So I kind of agree with them. We have the saw stops. And I talked to the students that the saw stops are probably the most dangerous equipment in here because they're the safest. They're the safest because they have devices where they're supposed to, like, if you have your finger or your hand in the way and stuff, the blade's supposed to drop down and not cut you. But when students leave our shop where it's nice and safe and it's kind of a fantasy land where everyone's trying to be protected, they go back to the real world and they get on their old rickety, $300 table saw or whatever it is. They don't have the bells and whistles. But they're so used to using our equipment, they tend to get their fingers closer and closer and closer and are more and more complacent with the safety equipment. And when they go home, they try to do the same thing and they cut themselves really bad. That's a problem for us. A big problem.
That makes a lot of sense. Okay. Took our safety break. Safety breaks are always important. It's probably instinct. I don't know, like, be a safety break. And on a job site, sometimes you do it. Hey, everyone take a
Stop
safety break.
everything, right.
Something happens, like, hey, let's, nothing happened here. I just got triggered a little bit looking at all the dangerous stuff. I'm like, oh, it's, damn, so they're just kids. Okay, let's go back here. Okay, team one, what did you come up with for, how do you find building energy performance?
Okay, so we focused on a small restaurant.
Mhm.
The climate, we depending on the weather. So if it was too cold, we'd probably turn on the heater. If it was too hot, the cooler. But then we started thinking about operating hours, because we're gonna start cooking early before the customers come in, at least some, food. So we said maybe around 7 a.m. If we open at 8 a.m., something like that. And closing, and we close at 10 p.m., we'll probably finish cleaning and still using the lights and some machines to 11 p.m., hopefully. So it's just depending. We also said, let's see, something that's not too low or too high in energy. So as well as trying to buy the machines that are not expensive as well, or I don't want to say expensive, but I want to say like they're just good use, that could help my business cost less in energy.
Okay.
So like I said, the AC, the heater, the refrigerators, the lights, maybe use solar panels.
Okay.
Great washing machines. And we were talking about control.
Yeah.
What are we able to control?
Yeah.
So, I can't control how many customers will come in. So how many orders, how many times I'll be using the stove and stuff. But I could control the energy in the building.
Okay.
So if I see there's not a lot of people, I'll probably turn off,
Oops. You have a VDC restaurant. This is an
Right?
example. I like it. What uncontrollable factor? I can't control how many customers come into my restaurant.
Correct, but I can control the energy in my restaurant. Let's turn off the lights. There's not a lot of people. It's so sunny outside. Let's open the windows or something.
Okay.
So what we came up with probably just analyze everything I just said, and that would determine the building, energy performance.
Very cool. I like it. The restaurant. Okay. Beat that.
You can't beat that.
I know.
Oh, we're up?
Yeah. You were hoping I just went over.
Yeah, I was. That's what it was.
We'll go.
We were talking pretty much to pick this classroom. So one way to make it, we thought about, operation hours. How long is the students are actually here? So we said probably like 7 hours. So what we would need to do, figure out how to, like this light's on, automatically go off. Have to know what it says. Could be sensors, could be, anything, something like that. Also, another thing that we could do, which is common, especially with the facilities, the new equipment that they're doing, our furnace, instead of kicking on at a certain time when no one is here, and when we need no one to be talking about something like, let's say, spring break or something like that. So that's one way.
Saving energy there.
Exactly. And a way to improve it and make it efficient, we talk about a metric, measure the electricity that we use, BTUs or electricity power, keep a record, compare that data, and maybe compare to other schools in the district that have similar equipment and see the reasons or ideas we can implement to make our building more efficient.
And we did a classroom commercial building. We figured we operate from 7 to 4. And we thought probably from 7 to 9, we just set the temperature at 70 because that's when it's not really hot. And probably from 12 to 4 is when it probably gets around the 90s or so. And we figured we would use LED lights, which would be more efficient. And we also factor in the life cycle of the cost of the equipment too. And we decided to go with the AC Seer 17.
Okay.
And I guess we got a little more sophisticated. We went to installation, to windows.
Good.
And what else am I missing?
Oh, math.
Go ahead.
So I was thinking that the system, I mean, with the commercial building, we should have a way to maintain the right humidity because you have humidity level that's too high. That much moisture would break down or wear out equipment such as water over there.
Okay.
So it would hinder the lifespan of those hospitals.
That's a good point, especially if this was the tropics. It definitely would. Yeah, I imagine everything was just with less stuff. Okay, good point. Okay. Yeah, taking into account the climate in the building for the equipment that's in the building as for the longevity of that equipment. That's a great consideration. Okay. So energy model. That's what we got. So why energy model? I think we've got this topic down. Here we go. In planning, design, and construction, you need to ask what's important to focus on, how much energy should we be using, and will we meet our goals? And in operations, we ask our systems performing as designed. What are the most impactful? What is impacting energy the most? What are measures we can use for efficiency? And what are the energy performance baselines? So we need to understand how the building will perform. What are the implications of energy of design features? For the design, we need to have a building to achieve energy objectives, and it needs to be based on data-driven decisions, which then enables a comparison of the as-built building to expected energy performance. So we've just introduced some new concepts in this slide. One of those is data-driven decisions. That's the first time we've used that term in this class. And this is also the first time we've used the concept of comparing an as-built building to expected energy performance. So what do you think data-driven decisions is? You want to take a popcorn guess? Yeah.
Well, you find out the best, the best facts of the building in terms of energy performance and go with it.
Let's say it again.
So like, you map out all the stats, statistics of
Guidance stats. Yeah, you're on the right path. If I resaid what you said, just say it a little bit differently, I would say I want numbers to give the answer I'm going to follow, whether that's or just simple, addition or just adding things up. That's data driven. That means I guess it wouldn't be, I guess a good example, maybe an architect. How does an architect design the facade of a building? Well, they think it's beautiful. That's the building siting I want. Is it data driven? But you could also do a data driven siting where you would say, well, why is that facade there? And you say, oh, well, we calculated the aesthetics of that for the community here in that region, and we came up with a very good index value. And this was the siting that met that. And you would get these. How it's data driven. It's not, art by number. You take the art out of it. But that's the idea. Is used. That could almost have a whole kind of should have a dedicated slide somewhere in this course. I don't think it does. I think that data-driven concept is just kind of sprinkled throughout it, and I think this might even be the only time it's ever used with that phrase of data-driven. So
The other concept here that's new is the comparison of an as-built building to the expected energy performance. And this one here, I know why they don't really go into depth in that. What you're seeing here is terms that come out of other classes that pretty much everybody would have taken at Stanford. And so these are concepts that, from the standpoint of somebody in construction engineering, they would recognize these terms, but I can see these are actually jargon for pretty much anybody else. So what do you think comparison of an as-built building to expected energy performance? So we have comparison. That's probably easy enough to figure out what that means. But we have as-built building. You'd say, what's an as-built building, and what is expected energy performance? Anyone want to take a chance on what's an as-built?
Well, you can,
Something that's right there.
yeah, you can look at the equipment that is in the building and how it performs.
Yes. So that's as-built. And the term as-built, like within construction engineering management, even sometimes takes an even more distinct meaning, which means when you finish building the building, you create the as-built plans, which means we had plans of what we were going to build, like in a highway. They said, this is going to be the highway grade. We went out and built it, but we're actually off by about 3 feet. And so then we turn in the as-built where we show what the actual highway is that we actually built. Same with the building. The windows change, the doors change. If you look in Psyche, the as-built has all that plastic stuff on the walls. That was in the as-built, not the original. So
could as-built be like the finished project? So it was like, it wasn't on the paper or whatever, but it's just finished. It's like that.
And what they do now, the more, say the VDC approach to as-built, is you bring in a laser scanner. And you put a laser scanner in the middle of the room, you stand back, scans the whole room. Gets all the ducts and the pipes and everything, and then that goes into the as-built model. So then when the next person comes in to remodel the building, they take the as-built plan and they start designing from that. But the other one is let's say we wanted to remodel this building. We say, where's the as-built? There's probably some paper plans somewhere, who knows. We could just come in and do a laser scan to start from that, which is then using just what's already existing in the building. So that's the as-built. It's saying what was actually done. And then comparing that to expected energy performance, what's expected energy performance?
What you predicted to have at that time, where you had a certain number already and you expect it to be what it is.
That's perfect. And the popcorn method, I'm going to tell John, where's John? Anyways.
Yeah.
His attendance has gone down. He had good attendance.
I'm going to use that term with my students, see the popcorn.
Yeah. So that is the comparison. So you take the as-built. So we take the building, like in the Y2E2 building we were all about. Take the final, what actually was built, the plastic walling and all that. And we run like an energy model. We would simulate that building the way it is. And then we would compare that to the original energy simulation. We'd say, is this building performing as it was built to what was expected from the original plan? Sorry, I made a mistake when I said that. I said you would run an energy model on the as-built model. You would also do that, but what you would also do is look at the actual energy consumption of the building. And you would say, okay, we predicted, say, that the Y2E2 building, and now I'm going to show my complete lack of understanding of energy industry, uses 1 kilovolt of energy. No idea what building actually uses. We'll say it's a kilovolt. And then you would say on the actual, so you look at what was predicted. So the predicted model, let's say it said this building is going to use 1.2 kilovolts, but the actual building is actually using 1 kilovolt. Then you would know that you're outperforming the model. But if the building is supposed to use 1.2 kilovolts and it's actually using 2 kilovolts, there's a problem. Well, I don't want to put a value judgment on it, but there's a problem, but it's using more energy than expected. So that is what's expected. And I don't think that's actually necessarily required of every building. That you benchmark, that you compare the actual performance of the building to the expected performance. The building's just assumed to perform as expected. Because on the Y2E2 building, my colleague, Tobias Miley, Dr. Miley, he did a comparison of the Y2E2 as-built building to the Y2E2's expected energy performance, and he found the Y2E2 building was using twice as much energy as the model predicted. And that was enough to get the paper. It was a big deal. So I know being at double, that's people weren't happy about it. Let's see. Data-driven decisions, chief energy objectives, implications. All right, so this is what goes into a BIM, an energy model. So we talked earlier, you talked about a hurricane. And the question would be, does a building use a different amount of energy during a hurricane? I don't actually know, but it probably does. I'm sure the difference between a sunny day and a hurricane day, where the lights are on more, buildings probably struggling. I don't know if hurricanes are, probably it's hot weather during a hurricane, so it's probably trying to air condition the building. Some pumps are probably running during the hurricane, and it's using more energy there. I know you were saying, also, with the building, I think we were talking like maybe the building sustained damage or something like that. But the same idea with energy, the building has to respond to that hurricane. So I have a BIM, and when it says simplified BIM, any ideas on what a simplified BIM is? It's just that's jargon in there. Simplified BIM. So the simplified BIM, it means you build a BIM, but you don't have all the details. You don't have every light switch, every wire. It's just like you take a mass, like a cube, and you say, okay, this cube is the building. Like at the simplest level, you could literally just say, this is a wood frame building with sheetrock and this type of siding on it, and run an energy analysis. So you probably get somewhere close to what it should be. You can be more detailed on the building and come up with different types of simplified degrees of simplified BIM. I've made a few of these, and they're fairly detailed, but it's not something you're going to build on. It's an energy BIM. You have the building system parameters. And so what this is now you take your simplified BIM and you add to that simplified BIM the equipment that's going to be in it. So what I would do is usually there's an equipment library. So I would click on the library and I would select whatever it is, those, looks like gas powered furnaces. And I would say, okay, there's what is that called? What's the name brand on this? This is a janitrol. I would select the janitrol furnace, 5,000 BTU or whatever that is, 50,000 BTUs maybe, probably quite a few. And I'm gonna put that in the building there. Maybe it'll even let me orient and point where it is, but I'm gonna put one of those in the building. This one has 2. And so now I have a building system and I'm gonna set the parameters that is gonna turn on at when it's, say, let's say I've set it for 55 degrees, I want it to kick on. Or I'm gonna have it kick on at anything below 55 degrees. And once it gets to 55 in here, just shut it off. And everyone's gonna be cold, but they're not freezing. And then I'm gonna take the weather data, because this building is here in San Jose, which is different than the weather in Reno, Nevada, which is different than Iowa, which is different than Florida. And so I have a software. I plot my simplified BIM in there. I plot my building components in there. I plot my weather data on there, and then it runs a simulation over the year. And based on that year, it gives me an estimate and says, with that type of system, heating this building in San Jose, this is your expected energy cost. And it should be plus or minus some percentage. If it's double, if it's off by it thinks your energy cost is going to be half of what it is or double what it is, that's not good. That's a really bad model. So I think what we're doing here is we're using an example. So if we take the research support facilities, and so here we have site climate, so that's the weather. We have the
energy system, the energy cost for that location, we take the construction cost. It looks like here we're gonna take, let's take the construction cost out. I'm not really sure why they're doing construction costs. So we have acoustic comfort, thermal comfort. Acoustic comfort is this room here. There's an echo. And if you pull the chair, it makes a loud screech and it echoes in here. So the acoustics in here aren't necessarily great. Thermal comfort, you know, I don't want to be freezing in here, but I probably don't want to heat this up to like an office building. Airflow and quality, this one here, it's really nice, has good airflow. These doors are open, and it feels like it has nice airflow. Siding had really bad airflow this week, or this week. And then we're gonna have materials and surfaces. Not 100% sure what that is for. I think that's probably what they're trying to say is material R factor. You know, every material has a resistance level, how long it takes to have one British thermal unit, which is a measure of heat, to pass through a type of material in 1 hour. So like this table here, if I put a block of hot steel and I put my hand under here, how long will it take for me to feel the heat coming through this table from the bottom side? And you know, you feel like if I put a hot block, it might take, you know, a while, you know. In fact, I might never feel the heat come through this table. If I put something hot on here, I'll feel it. So that's everything has a resistance. If for example, if I put something hot on this glass, and I put my hand underneath this glass, how long is it going to take me to feel something hot coming through that glass? Like that. So that's the difference between glass and silver. And so we have all these inputs in there, which it looks like the same ones on the left. So they're just saying all this goes into the building. Let me get a little closer so I can see this. So this one here they're doing in Excel. I'm not going to just to give an idea of how this works. So eQuest, I want to point out eQuest. That's energy modeling software. I'm pretty sure eQuest is a free software put out by the U.S. government, Department of Energy. And so what that is they through universities, they've all collaborated together on this software. You go online, download eQuest. Not eQuest, is one called DOE2, the Department of Energy #2, DOE2. And so this software here, you then build out your model. I honestly don't know what all this Excel stuff in here is. I don't do energy modeling. I have done some, but I never got past eQuest, so this is much more advanced energy model. To tell you the truth, this is probably how Professor Fisher feels when he looks at my scheduler diagrams. He's probably like, are you kidding me? There's really 12 different boxes in this diagram. Why don't you just have one that says schedule? But it's clearly all important. And this box here is really big, so I'm guessing that's the important part. And that represents this building as a model. There we go. Coordination between design and engineering. I didn't color coded, so let's see if we can figure out which one of these boxes is design and which is engineering. Anyone want to take a guess on that? Daylight and schedule. That's probably a design feature. That's architecture. Engineering. Here we go. I'm starting to decode it. The orange ones, natural venting. That's probably engineering. Heat recovery. That looks like engineering. Transpired collector. And it sounds like collecting up to people who transpired. Doesn't sound very good. Okay, so I can see here, so coordination. I think what they're trying to say here, see if we go to the next one. No. Is there's a back and forth between the architectural and the engineering. The architect designs the building, the engineering says, you know what, a glass wall pointing towards the sun is not a good idea for this building. I think you should have some less glass. Architect comes back, says, okay, there's a little less glass, what does it look like, what does it look like? Until they come up with a solution that has less glass. That could be what it is here. It is showing this building doesn't have a lot of windows on some side. And that's probably going to reduce the solar. So building energy model is supported by various information sources. This one right here, I want to point out, this natural ventilation, that was the Y2V2 building. That's why the Y2V2 building performed so badly, is because when they designed that building, there was no good way to estimate natural ventilation. Basically, the only way you do natural ventilation is you model the building as though it had a just gigantic, I guess what it's called, an economizer, is that basically the building had a huge amount of natural ventilation coming in. So you trick the model into a naturally ventilated building by telling the building you have a huge fresh air intake. Because nobody had built this, had written software to represent that the building just literally had that hole in it and wind was blowing through it. The daylighting, that one there with the Y2V2 building, it turned out the R factors for the glass windows was basically made up, but not made up. But they would take the most perfect window that they could manufacture, they would submit that for review, and be given an R factor from the lab. R factor being resistance. If you have double pane glass, it has a different R factor than if you have single pane glass. But the thing is once I get my glass, an R factor from it, and then I go and start manufacturing. When I manufacture, each one's a little bit different. They're not the same level of quality. So if I have this idealized R factor from a lab for this piece of glass, and then I bring in the mass-produced glass, which might even be the same glass that was submitted to the lab, nobody comes in and checks on it, and I put that in the building, it's going to have a completely different performance than what was expected. And that was one of the things on the Y2V2 building. It turned out the windows in there are not the same windows that were used in the model. Oops. So there's building geometry, the materials. I have no idea what fenestration is. That is definitely a technical term. Heating, ventilation, air conditioning, HVAC, domestic hot water, plug loads, lighting. Lighting is important because lights put out heat. These lights up here, if you touch them, they're probably warm. And they have occupancy. And humans are simply little heaters. Every human being puts out heat. You put enough people in a small enough space, it gets really warm. So that is one of the factors in there, especially for an office building. You have a large number of people trying to put the most clerical workers you can into a room to work. So this is showing as you go into what's called the level of detail 100 model. I don't think it uses level of detail 100, but that would be, they're using there's called a 10% model, 25%, 50%, 80%, 100%. What do you think that concept is there where it's going through these percentages? Any ideas? Yep.
This is called agency completion. 10%
Completion of what?
Building design.
That's correct. So it's 11:30 right now. And the class officially ends at 11:30. Usually we've been ending at 11:15. We have 5 more slides. So I'll go through these pretty quick. I'll probably go a little bit less to the back and forth on the question. A little less than popcorn. Let's use popcorn, a little more than
Hey, Forrest,
yes.
I haven't seen any of those slides on the thing. I'm looking at it. I'm looking at you, but the slides are fuzzy, but it's not producing the slides.
Let's fix that.
I just, it's like I'm listening to you, but I'm missing all the, it looks really cool.
Okay. Let's take care of that first.
Does it class end at 12 first, and not 11:30?
It's funny because it shows slide 17 on there, but it's just blank.
Reading view.
Yeah, that's a
Second, let's share this again. I might have hit, I think what I did was I pressed, there you go, how's that?
Oh, thank you. I could see.
You're welcome. I pressed,
Does yours say building energy matrix and energy?
yeah, it does. I'm gonna click all the way through it real quick. What it was, I was on
The other one?
I used presenter view. I gotta keep remembering.
Yeah.
Zoom
Yeah.
is limited.
No problem. Thank you.
What was the question? Oh, yes. Well, they have an official time class supposed to end. I know we had planned to go to 12 originally when we designed the class.
Yeah, that's beautiful. I can see it.
Everett Valley College changed that to 11:15. They were trying to say so the class would meet, or no, they changed it to 11:30. They wanted the Tuesday, Thursday, Saturday classes to be the exact same length. They didn't understand we wanted short class, long class. They tried to have class. So we're making the most of it.
Okay, so Saturday class is from 9 to 11:30 then?
What's that?
9 to 11:30 on Saturdays?
Yes, that's what I think that's the official, what it's saying on the internet now. Actually, I think the class. Wider, back up forward. Now it's going to give you the last 5 slides and you go with funds probably. Now I can't see what the next one is either. Okay, so you have the absolute correct answer. It's degrees of completion of the design. I don't know who made this graphic either because that's a pretty small print. But just like this building here, what I did the back of the envelope estimate of the energy consumption, that was like literally level of detail 5%. There's like no real design. Oh, it's probably this, this, and this. Plus or minus half to twice. As an engineering thing, I'm probably in the ballpark. So as the design goes further along, and this little wood building here where I can look at it, goes to a Revit model. Now with the Revit model, that's probably this level, it's like 50%. And then if we put all the materials in the Revit model, the different types of equipment that are going to be in the Revit model, it starts getting closer and closer to 100%. My back of the envelope design for this is somewhere between what I say, $12,000 and $48,000 to keep this. No, I said $48,000 and $96,000. I think it was 48 and 96 was the range. It was like this building to put the interview. Assuming it doesn't have solar. That number of somewhere between 48,000, 50,000 to 100,000. That number is going to get narrowed as my design gets better. Let's say in my apartment, I think I pay $100 a month, but that's water and everything. But let's say it costs $100 a month, so that's $1,000. Let's say $1,000 a year for electricity and water, sewer equipment. I don't think this even has a sewer. This doesn't have water, it's just electricity. But let's say it did. Let's say it was actually a structure. And that's probably the size of my apartment. How many square footage is it?
They come up, that's 12 by 16, so about 170 something.
Well, what's it's going to be
192.
102.
how much?
192.
192 square feet.
12 by 16.
Yep,
Okay, that's pretty small. My apartment's big.
it is.
So that's definitely not going to cost $100 a month. Let's say $20, maybe 40 at most. But just for the numbers, let's say it's 20. So let's say $200 a year. So that's $2,000 every 10 years. That's going to be $6,000 for the energy cost. So that's well outside of my estimate of 48 to 96 by a huge amount. Okay, that's probably because this isn't a typical building, and that's why that 80%, 20% rule clearly has it. So there you go. Then you'd be like, well, where did that number go? Well, it clearly isn't meant for this. There we go.
So now I kind of check my numbers, fact check. Like, well, I know it's not gonna cost $100 a month. And even if it was $100 a month, that's gonna be, say, $1,000 a year, which is gonna be $30,000, but I'll be close to $30,000 a year. I mean, $30,000 over 30 years. Yeah, which would be about $100 a month in energy costs. So, it could be $100. I don't think that is the cost. So we know it's not going to be 30,000. So it's somewhere else. You can start seeing how you start playing around with the numbers. But at some point, I can push a button in Revit, and that model would give me like 2 of what it probably is. Of course, assuming electricity prices. So this is like the Y2E2 building. I really can't read this print. Whoever built this clearly knew what they were talking about. Because energy model, calibration, as-built energy model. Okay, so what this is saying, so this is your as-built. We talked about the as-built. So you've gone through, I think what it's saying here is you're at 100% of design. After 100% design, you have as-built. You do what we actually built. What was the final? So you create a new model, as-built. Then what it's saying here is now you go through calibration. You say, okay, let's change the set points and get the two of the building so it actually works. Here's where John told me to try to figure out examples and speak to the students. I would talk about here about a carburetor. I don't think anybody here is going to understand. What's something that usually you have to tune? And when you get it at first, it just doesn't quite work. You got to fine tune.
Drone.
The drone. At first, it doesn't fly. It takes a while to do it.
When we took the drone out there, we had it calibrated, didn't we? Yes.
Okay. So drone calibration. Definitely not carburetor. So this drone, if I take it out of the box, doesn't fly. It takes a while for it to calibrate. What do you use for calibration on it?
Actually, it was a different one. That one had a problem, so that didn't work. But so pretty much we just need to tell it, put it on a flat surface, and it's real simple.
That's right, yeah.
So
it has to know where the ground is.
exactly, just to know, yes. And it actually lets them know, like, oh, this is ground zero, pretty much like a altimeter type of thing.
Okay, perfect. There it is. Calibrate the drone before you take it off. You sit there, you hit the button, you flip the control, go, then you can take it off. If you try to take it off before that, it'll do all kinds of things. So the same building's the same. When you first turn on the building isn't going to work. It's going to be, it takes time to calibrate the building. Then you have a building, you have a calibrated model. You have a building with the set points, rerun the energy model to look at the building with the actual set. So this is an example. This is a pretty standard graphic for teaching this. I haven't had the energy analysis class in 2006. It's been 12 years since I've taken the energy analysis class. Luckily, I've been able to keep up with this by watching other people finish their PhDs, watching their presentations. And so I know that usually you have a graph, you say, hey, look, this is what we thought it was going to be. Now, this is what they think it is, because look how regular it is. Boom, 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 because that's model. That's an expected cycle, probably per year. So or that could be daily. Kilowatt hours, 500 kilowatt hours. You know what? I can say that was year, day, or hour. I wouldn't even think it. But anyways, you get the idea that this is like probably per day. It's got the up and down, or that could be weeks. I don't know what this time scale is here. This is the weekend. That's like just because of the length of the downtime compared to the length of the downtime. I bet you that's weeks. And so when the building's being occupied, it's saying that it's using 200 kilowatt hours more than when the building's unoccupied. And that was what was expected. This could be over a year. Just look at the curve. I just don't know the timeline. no way of knowing. When you do a graph, always label your axes. I know that's kilowatt hours. Whoever did this just assumed that anybody that's not an idiot would, of course, know what this is. So I am literally the idiot who has no idea what this axis is right here. So, what this is showing though, and what is important, is that the actual measured data of that energy is much different from what was expected. This building here, in fact, is using 20% of expected energy. That's really bad, because if you thought the building was going to use this much energy, and you designed it and you built it, and then you found out it actually uses this much energy, that means you way overestimated. You put way too much money into that building, because now you have a building that's a higher quality than what's expected. So now that's like saying, I need a car. They'd be like, what kind of car do you like? I'd be like, I don't know. I want it to have 4 doors. I want it to get me from here to work. I want it to be efficient. Maybe a Honda, a Kia. And then they give me a Lamborghini or a Ferrari. And I'm like, that's not, and they go, well, it's okay. Just, it's $100,000. But I was going to pay $10,000. Like, well, you got a Ferrari. That's a problem. This is the Ferrari of buildings. When they were expecting a Ford Focus. But that's actually, legitimately, that's the state of energy model. You know, it's not cost estimating, it's not scheduling, this is energy analysis. So you get a ballpark idea. You can see, I mean, it doesn't even show the ticks on it. I don't know what this is. But having seen people's PhDs, their presentations, they're describing the difficulties of modeling what an energy does. Yeah. That one's way off. So, optimizing the energy model is an iterative, data-driven process. So this, you remember Filippo, when Filippo talked, he came in and he talked about optimization. And so when you talk about optimization, what you're talking about is using different types of algorithms to take that building, that energy model, and looking for the best solution. So you take a building, I think that's building energy model, building BMS.
Building management systems.
Building management system. Okay. So I think this is optimizing the building after it's built. This is the calibration process. So you take the building management system, and based on the building energy management output, you can look at how the building is performing, and there you start changing the set. You can do that through trial and error, which is how it's normally done. I don't know if you're saying here there's an optimization software that'll go through, and what it would do if this was optimization, only because I've worked with a little bit of optimization software, is you would take the set points of this building. So what we would do here, we take energy use, and here we would take set points. So let's say I want to look at the cost of that heater to heat this building. So I can go everything from, say, a set point of 30 degrees, make it 32. So I go from freezing. And so I'm going to turn that on when it's 32 degrees. All the way through, I can turn that on. Let's see. If we started heating the building below 32 degrees, or I start heating the building when it's below 65 degrees, it's California. We don't want the building cooler than 65. So where do I turn on the heater? My energy use, when it turns on at 32, is going to be low. But if I turn on the heater, did I get that backwards? I'm going to heat to 32 degrees, and then it's going to turn off. This is going off. Or I'm going to heat to 65, and then I'm going to turn on. My energy usage will go like that. And probably just because of the design of this building, it's probably actually going to go something like this. It's going to start costing a lot more. So I can figure out those curves, and I can set the system because I want to know, I want to minimize I want to optimize the heating of this building to get it to 65 degrees. And so I can run a software algorithm on that, the control for this unit that's going to turn it on at different points and turn it off at different points, measure the actual output, and then we'll just cycle through. So for a week, this thing will just turn it off seemingly random. In fact, it actually could be random. It would just randomly turn on and off, measure what the result is, and then it would go back to the set point that gave the best output, and it would just stay at that point. Rather than somebody coming in here and understanding the building and what they're doing, and trying to say, oh, this would be what's. Okay. I think we covered this one here. For a school building, how would you define energy metrics? Relay these metrics to the design team. Use energy modeling during design to meet these metrics. Use energy modeling after occupancy to assess if the as-built building meets the expected energy performance metrics. And who from architects, engineers, construction, and operations will be involved? Do we have time for this? We have 10 minutes left in class. I can put that up to a vote.
That's fine.
Yes? Stay? Stay? Okay. We'll work out a.
Okay, so, we were doing 75 minutes.
Oh, it's on the questions or?
Yeah.
All right.
Anyway, so we were talking about the classroom. Our building had to do with measuring the kilowatt hours per student and per square footage. And so our metrics were to take data, current existing data, with our current existing equipment, which is whatever we have our natural furnaces and stuff, whatever AC units. And then was that, then we call that as is. That's built. That's built. And from that data, we compare with this building, maybe if we can have external sources like another school that has the same equipment or something similar, we compare their efficiency versus ours. Once we got our as this model, improves what we can do to it. What can we do to it to lower kilowatt hours per student or per square footage? And that would be like, add solar power, insulation be another one of those. Sensors on our light switches, come up with maybe a combination of those, which one is more visible and taking into account the cost of the pros and cons from one system to the next.
We also have to run it out over a period of time so that we can actually measure.
Okay.
The improvements.
Collect data and be able to measure
To measure your actual performance, how are you going to measure actual performance?
Measuring the energy usage.
Okay. And use the same metric as, what was your metric for per square footage, per student? What was-
we actually like one per square foot,
Yeah.
basically this is actually the building, and another one per student. So if we use in a building, but it's occupied by, 3 students versus 1 student,
Okay.
obviously the efficiency decreases because we have more students using that same amount of energy.
And your integrated concurrent engineering team, who are you going to invite to that meeting?
From our as is to our final, after we do our manipulations and stuff to improve it,
Yeah.
we will have the stakeholders that have in place and the input says, so like pretty much less than we have the installation installers, our solar panel installers, so we can discuss which takeovers are going to take place in improvements. And if we're going to do that, who's going to go first, so we're not in each other's way, and so we can coordinate the actual, because everybody's in the same place, making the same move.
Okay.
Architects, engineers, operations.
Operations. Very good.
You guys want to go?
There you go.
Can you repeat that?
It's good.
Okay, so while he's drawing that, so we focus on the kilowatts per hour, which will be per student. So our design will be creating, or having sensors to detect how many students come in, or how many people come into the school building. We also will have the lighting sensors, so as we're walking in, or, depending where the tables, the chairs will be after the students, the lights will turn on. And as well, we will have solar panels to help with the best cost. So the people who will be involved in our meeting will be electricians, engineers, the client, if it's a principal or somebody in the district, general contractor, the solar panels installers, or the people that will apply the sensors as well. So for the way the graphing, but if I'm understanding, so we have, this is what's happening right now, is that it doesn't matter how many students come in, it's still you're costing a lot. So it doesn't matter if you have 5 students, the whole building is being used. So the lighting, as if when we add the design and everything goes through, well, the sensor will detect how many students there is, and that will determine the list, how much the cost will be, something like that.
Okay. And let's see. Who will you invite to the integrated concurrent engineering meeting?
So I think I said the electrician, the client, the general constructor, the solar panel who install it, and the sensor who install it.
And Roger and Matt, the operations team,
Yeah.
who did the facilities.
But yeah, so basically, like I said, it doesn't matter how many students are in the building, you're still wasting the same money. But if we put the sensors, the solar panels, we can determine how many students as they come in. I mean, that'll be the energy and the cost of the building.
Sounds good. Okay, David, you guys are up.
Want to go next, or you want to go?
No, you go. You take it over. I'll sit back and.
Our plan is, we did the solar panel, first kilowatt hour per square feet over months. We figured our solar panel would cost around $25,000 to install in the state of California. So we figured our monthly bill would be around $450 a month, about average. And we figured it'd be maybe a 30% reduction. So what we did was we took $450 per month times 0.30. We came up with $135. So we took 450 minus 135. We came up with saving of, or reduction of 315. We took that times by over a year span, times 12, and we came up with 1620. So that's how much we would save per year. And the benefit of this would be a tax write-off for us. And also reducing from 25,000 to get our cost back. We took 25,000 divided by 1,600, came up to about 15 and a half years to get our cost back. And we also figured we could reduce that to 10 years with a tax write-off. So that'd be a beneficial to us. Not only that, you add more value to your house, to your house by adding a solar panels, which is increase your assets over time. And sooner or later, it'll be a California compliance. So every house in California will need to have this. And I figured for our who we would need our contractors, engineers, PG&E, because they were the ones who give you your tax write-off. And of course, our solar installers, they're the one who will verify whether everything is up to code. Am I missing anything?
What's the chart?
Me.
So to obtain overall performance of the school building, we found a way to actually detail that. First, you take how many kilowatt hours of the electricity bills from PG&E, graph it over a year span, right? And on this graph, it looks like kind of a bell curve because during 6 months, which is during summer, you will use more energy. To heat up to cool your building. That's sort of the hot summer. That's what it looks like.
I see. So that's the June. That's the cooling load.
Bell curve is in the wintertime, right? So you're using more energy in the wintertime because there's less solar light, right?
So that's the winter. Show the months. Where's May? That's June. I got it. Okay. So you're using more energy in the summer. Okay. So you don't have a heater in the winter.
No, but you have an air conditioner.
There you go.
So
Or
just
baseline, and the cooling load is that much more than the heating load, which in California is probably not bad as
Yeah,
well.
I think you're right.
And so this is a retrofit you're doing, right? To change the heating cooling load, the energy usage.
Yes.
Okay. And who are you going to introduce? Who are you inviting to your integrated concurrent engineering meeting?
It will be the solar installers, the PG&E people,
Yeah.
and engineers.
What about Matt and Roger? The facilities for operation?
didn't think of that.
Didn't think of that?
They're your end users.
End users, yeah. Invite the end users.
Well, I guess the owners, yeah.
Yeah. Any questions or feedback? That's good.
One unrelated. Hi. What kind of solar panels are you going to use?
Oh.
What company are you going to use?
Somehow.
There you go.
Yeah. All right. Thank you, everybody. We'll be back on Tuesday.
Thank you, Mr. Lomax.
Thank you.
Take her easy, Dave.
Hey, Dennis.
Yeah,
Hey, I got to give you a call a little later.
yeah,
Got to ask about a instructor.
no problem.
Thank you.
I gotta get on the road anyways.
Hey, take care, Dennis. Good to see you.
Yep, take care, Dave. Thanks, Forrest.
All right. All right, Dave. Turn it off the meeting.
Okay. You're not going to go around? You don't want to see the house?
Oh, that's right. That's right. That's right. Yeah, here. That's right. Let me put the overhead projector back on.
You going to show YouTube or no?
Thank you for it.
That's why we need those smart screens.
What's the trick for turning this on? Oh, there it goes. It takes a minute to warm up. We're gonna do a quick tour of the house here. There we go.
You ready?
Yeah. Let's take a look.
We're going to walk outside. Can you see okay? It looks blurry to me, but. Oh, Bruno, don't go anywhere. Holy cow, my computer's hot.
The sun came out during the class.
Can you all see this here?
Yes.
So we put this window in. This is a highly efficient window with a double pane window, but this is how you do flashing. You have to put your Tyvek on first. And this is all going to be inspected from the inspector to make sure you got your proper flashing on. And Tyvek. Come on in here. Last time I showed you guys, now we have the walls all framed up. The bathroom, this is the garage over here. And we also put this wall right here. This is the existing garage. On the other side there, and they didn't put any insulation in the walls. So I have to use an Artec, well, it's an Artec foam insulation. Gives you 3.5% R factor in there. So I tacked that on. And the nice thing about this Artec foam is that these are water pipes. So if this gets wet and stuff like that, it's not going to ruin the foam insulation or anything like that. And this will get insulated with regular insulation. So that will cover all that. Come on around. We put the shower in. I don't know if you guys can see that. Start the shower. You do that before you sheetrock. Put all the special backing on there so you can screw the sheetrock in. You can see all the water pipes in there. Does anybody know what the colors mean? There's blue and red. What does that mean to anybody?
Hot and cold.
Hot and cold. Why do you think the blue is on the bottom and the red is on the top?
Because hot air rises.
Good. Good, because a lot of people don't know that.
I didn't know that.
Huh?
No, nothing.
Yeah, no, I'm saying you didn't know that, but you know, I know just because from engineering that small things like that over time, yeah, for 30 years you're heating your cold water, it'll make a difference.
Yeah, exactly.
Is that insulated? It looks pretty thick.
This here?
The pipe itself.
No, it's not insulated. It's really good quality. I got a really good plumber. He's using the best quality for this insulation. But take a look at this. Is really interesting. Now, this is going through walls, right? This is a 2x4. Look at the holes.
They're pretty good size.
And you have to put the metal plates on here, right?
Striker plates.
Protect that in case you screw sheetrock in there. You don't want to hit those pipes. But look at this over here. This wall right here is a 6-inch cavity in between here. This is like building walls like this. So now you can run your pipes and all your ductwork through this wall right there, and you don't have to worry about screwing through the pipes and all that. It just makes it a lot easier for plumbers. So there's a lot of advantages for having like a secondary wall in there for plumbing. And you can see look at all the work the plumber has to do. Look how many holes he's got to drill or she's got to drill. Opposed to no holes over here. All I'm saying, folks?
Yeah.
So that's pretty much it there, you guys.
Okay. It looks good.
And this is the outside pipe. Look at all the holes that he's got to drill without that second cavity wall. It's a lot of work. That's pretty much it for us.
All right, thank you, David.